Constructing antiderivatives graphically and numerically is what we want to talk about here. Graphically and numerically. It's a pretty important subject. Let me put it, as I did with a problem last time, in the context of statistics. I will come back to physics on Wednesday, but for today, let's talk more statistics. Now, we talked about statistics last Friday in the context of the normal curve, or to be more precise, the standard normal curve. Let's do a different curve this time. That's going to be a statistical model for us. Let's pick a particularly simple curve, actually. Let's pick a curve that is constant at 0 up until I get to 0, where it's going to have a jump discontinuity and jump up to a value of, let's say, 1 when x is 0, stay constant at 1 until x is 1, where it will jump back down to 0. So kind of a strange function. You could write a piecewise formula for it. F of x is going to be 0 if x is less than 0 or x is bigger than 1. And it will equal 1 if x is between 0 and 1. This piecewise function that is discontinuous at 0 and 1 turns out to be a pretty useful function, even though it's not continuous and not differentiable at 0 and 1. It is the graph of something called you could call it a standard uniform distribution. Standard uniform distribution. It is the basis for random number generators in many computer programs, including in spreadsheets. Let's actually go ahead and open up a spreadsheet here. So you can do what I'm about to show you either in Excel, which is a Microsoft spreadsheet, or Google Sheets. If you type in a spreadsheet equals rand, parenthesis, and maybe also end parenthesis, it will give you a random decimal number between 0 and 1. There's the output. If I use it again and again, it will give me different numbers every time. How am I using it again and again? Effectively, I'm copying and pasting over and over here. Control C, Control V, Control C, Control V, to get a bunch of different numbers between 0 and 1, random numbers. I can also get a bunch of them by copying and pasting the formula downward. There's a bunch of random numbers between 0 and 1. How are these numbers picked? Partially, it's an internal thing that I'm not going to get into. But effectively, mathematically, these numbers are picked according to this uniform distribution on the interval from 0 to 1. Effectively, over any interval, any subinterval of 0 to 1 of a constant size, say of size 0.1, just to pick something specific, say from 0.6 to 0.7, the proportion of numbers I get out between 0.6 and 0.7 are going to be the area under the curve there. Hey, area under the curve, calculus. What's the area that I actually don't need calculus because I can see it. It's a rectangle, base of 0.1, height of 1. The area is 0.1 or 10% if you prefer. 10% of the area, 0.1, is between 0.6 and 0.7. And because this distribution is uniform, that's the same area as I'd get over any other interval of length 0.1, like from 0.2 to 0.3. A little hard to see there. I'm sorry. That's a 0.2 there, and this is a 0.3. That also has an area of 0.1, 10%. The point is, over any interval of length 0.1, I should expect about 10% of the numbers to be between those two given numbers. So for example, let's go ahead and illustrate this. Let's get 100 numbers between 0 and 1 here. By the way, every time you do a copy and paste, the numbers change. There's 100 numbers between 0 and 1. What percentage of them are between 0.6 and 0.7, for example? Or what'll be easier to program is, let's say, less than 0.6. Equals count if in a spreadsheet used in this way, C1 colon C100, comma, say in quotes, less than 0.6. That's going to count the number of numbers that are less than 0.6. Should be around 60 of them. You can see it's saying at the output 64, but if I enter this, it'll change because all the numbers will change. 55, if I copy and paste again, it'll be a new simulation. 57, copy and paste again. 59, copy and paste again. 63, copy and paste again. 52, okay, I can do this over and over again. Sometimes it's close to 70. But generally speaking, it's close to 60. We got exactly 60 just a few simulations ago. Because of randomness, it's not exactly 60, but in the long run, about 60% of the numbers will be less than 0.6. And yes, about 10% of the numbers will be between 0.6 and 0.7. This uniform distribution is effectively what's being used to create that random number generator. It's an example of what is also called a probability density function, or just density function if you prefer. Probability density function. PDF for short. Or if you're just calling it a density function, you could call it a DF. Effectively, the height of the graph near any point gives you the density of the simulated data near that point. Say that again. The height of the graph near any point, like 0.6, for example, gives you the density of the data if you got a lot of data points near that point. If you got a lot of data, the density value here near any one of these points is 1. And effectively what that means is if you create rectangles like this and multiply the length of the rectangle, the base of the rectangle, call it delta x times the height, it'll give you the approximate percentage of the data points near there. That has more significance if the graph's not constant. If the graph goes up or down, if it's normal looking, that has more significance, which I'll explain more later. You can use this to model probability as well. If I write an expression like this, P of 0.2 less than or equal to x less than or equal to 0.8, for example, that is a symbolic way of saying what's the probability that my data point is between 0.2 and 0.8. You might want to write that out. That's a symbolic way of saying what's the probability that my data point's between 0.2 and 0.8. And the way these density functions work is that you find that probability by integrating the density function over the given interval, 0.2 to 0.8. What does that equal? For this example, well, f of x, when your x is between 0.2 and 0.8, is 1. I'm integrating 1 from 0.2 to 0.8. I'm going to get 0.8 minus 0.2, 0.6. Keep picking 0.6 today. The area under this curve between 0.2 and 0.8 is 0.6, 60%. By the way, maybe you notice the area under the entire curve is 1. That's a necessary thing for probability density functions, is that the area under the entire curve is 1. Modeling things with probability is a very important thing in statistics. This works because we define it to work. We want our density function to model a situation like with random number generators, so that this really does give you the approximate percent of the time that, in this case, your number is between 0.2 and 0.8. Being in an integral, we were able to compute it with an antiderivative. Can I do that in general, even in more complicated situations? Yes, because what I can do is I can take any probability density function and create a cumulative distribution function. I went from lowercase letters to capital letters. That's okay. CDF. I guess that's actually a nice coincidence, because that's like going from a derivative to an antiderivative is going from a lowercase to an uppercase. Nice coincidence. What is the cumulative distribution function? Call it capital F. That's meant to be suggestive. This is going to be an antiderivative of little f. It's effectively the probability of observing a data value less than or equal to little x. Let me write that out in words. Probability of observing a data value like a random number less than or equal to little x. For our particular example, this uniform distribution, we could write that like this. Well, okay. Let's see. I'm going to use a different letter here. I'm going to use a capital X. That's actually traditional. And the lowercase x here. It's this probability. Think of this as a random data point. And think of x as a particular number. That's going to be the integral of that density function from 0 to little x. And maybe I should call this capital X dx. This is a little weird, but don't worry about it. In our case, that's integrating the constant function 1. Just like before, you get an antiderivative of capital X here in this case, going from 0 to little x. That's going to give you little x minus 0 is just little x. Now that's, you might be weirded out by this, okay? Like, why am I using a capital X? It's somewhat traditional, okay? Think of capital X as being the random data point that you don't know what it is. Think of little x as being a particular number. By analogy with what I did up here, where I integrated the PDF from 0.2 to 0.8 to find this probability, this area under the curve, I am now integrating from 0 to an arbitrary number, little x. If little x were 0.6, I would get 0.6. I can think of this as a function of little x. And notice that its derivative, capital F prime of little x, is 1, which is the value of little f of x, if little x is between 0 and 1. That's not a coincidence. We have constructed, in this application at least, an antiderivative of little f. Actually, we can expand this to include values of little x that are bigger than 1 or less than 0 even. If I let capital F of little x be the integral from 0 to little x of little f of, okay, I'll go ahead and use a capital X again. This is weird, but I'll do it. I can even interpret what this means, even if little x is bigger than 1 or less than 0. Let's think about the case where it's bigger than 1 first. That's a little easier. Again, this is little f here. What if little, here's, oh, this is 1 right there. What if little x is over here? What if that's little x? what will be this integral from 0 to little x of this function? It'll be the area under the curve. The area between 0 and 1 is the area of this rectangle. Base times height is 1 times 1 is 1. The area from 1 to x is 0. There's no area there. So if little x is bigger than 1, this has got to be 1 plus 0, 1. What about if little x is less than 0? Negative. In this picture, what if little x is over here? That's kind of weird. I'm integrating from 0 to little x where x is negative, but we did talk about this last time. I could think of it as the opposite of the integral where I switch the limits of integration around. However, this example is both strange and simple at the same time. Little f is 0 over here. The area under the graph from x to 0 is 0. This is negative 0, which is 0. What I've done here is I've created a piecewise function, capital F of x, that is 0 if x is negative, leave some space, 1 if x is bigger than 1, and x if x is between 0 and 1. And if you graph this function, its graph looks like this. 0 over here, 1 over here, and linear in between. And that is a function such that wherever it's differentiable, its derivative equals little f. Capital F prime of x equals little f of x for all x where capital F is differentiable. Now, there are two spots, two values of x where this is not differentiable. I hope you can see them. 0 and 1, there are corners in the graph. So f prime, capital F prime of 0 and capital F prime of 1 do not exist. Oh, but that's not so strange when you think about it, because little f is discontinuous at those values of x. Again, we have constructed an antiderivative of little f by thinking about an integral. That's a little bit of a twist on the fundamental theorem of calculus, isn't it? With the fundamental theorem of calculus, we had an integral that we wanted to figure out what it was, and we used an antiderivative to figure it out. Here it's the other way around. We're using the integral and thinking about areas, effectively, to figure out an antiderivative. Well, I did use an antiderivative there, but I could have thought about it with areas. You see the difference? Again, before, got an integral we'd like to evaluate, use an antiderivative. Now we are using the integral to define an antiderivative. This is super significant, actually. People, even when they've taken calculus, though, don't fully appreciate how significant this is. Integrals are more than just for finding areas under the curves, because they have some application. They are important for that, but they are also important for defining antiderivatives, because those antiderivatives might be important in some application. Effectively, they're equivalent. Finding areas and finding antiderivatives are equivalent, is the idea. That, again, was Newton and Leibniz's great discovery. Let's do another example. This time, let's consider what's called a triangular distribution. Triangular distribution. Another density function, or probability density function if you prefer. Let's once again make it take on positive values between 0 and 1. The graph is going to look like a triangle. That's why it's called triangular distribution. And in fact, I'm going to make it an isosceles triangle. I'd like the total area under this to equal 1. That's what is necessary for it to be a valid probability density function. Want the area to equal 1. Well, that area is the area of a triangle. 1/2 base times height. The base is 1, b is 1. In order to make that area 1, what's the height got to be? Hence, the graph's not drawn to scale. If the base is 1, the height's got to be 2 to make the area 1. I'm trying to just choose the height so that the area is 1. This equation means the height must be 2. This number right there must be 2. It's not drawn to scale on these different axes. If I choose this to be 1, that will have to be 2 for this to be a valid probability density function for the area under the graph to equal 1. In terms of a formula, it's a little trickier than the uniform distribution. I can certainly say it's 0 over here and over here still. 0 if x is less than 0 or x is bigger than 1. But in here, between 0 and 1, it's got 2 different pieces, right? 2 different straight lines make up the graph. What are the formulas for those lines? Well, I need to figure out the slopes, don't I? The slope of this one is what? Rise over run. The rise is 2, the run is 1/2. 2 over 1/2 is 4. Slope that is 4. Slope of this one looks like it's, by symmetry, got to be -4, right? Yeah, the rise is -2 and the run is 1/2. This is -4 in slope. If that one's got a slope of 4 and it goes to the origin, it's got a y-intercept of 0, its equation's got to be 4x. 4x if what? If x is between 0 and 1/2. This one has a slope of -4, but the equation's not -4x because its y-intercept is higher. If I drew this line backwards like this, you can see it's going to have a y-intercept up at 4. Now, that's not actually part of the graph. I just did that to help me find the formula. The formula is going to be -4x plus 4 if x is between 1/2 and 1. That function, that little f of x, is a valid probability density function because the area under the graph does equal 1. Finding areas under this above any interval from some number a to some number b, let me pick particular numbers like 0.4 to 0.8. Finding this area will find the probability of a data value being between 0.4 and 0.8. That area, whatever it is, it could be represented as an integral, will be the probability of observing a data value between 0.4 and 0.8. It'll be the percentage of the data values between there if you've got a large enough sample size. Now, we could find that area, if we wanted to, by using the fundamental theorem of calculus. Maybe we should. Let's go ahead and do that. Let's go ahead and practice a property of integrals. Since the formulas for these 2 pieces of the graph are different depending on what interval you're going to do, I'm going to break up the integral into the sum of 2 integrals, an integral from 0.4 to 0.5 plus an integral from 0.5 to 0.8. There's an example where that interval property of integrals is useful. In this case, the formula for f of x is 4x. In this case, it's -4x plus 4. Now I'll use the fundamental theorem of calculus. Antiderivative of 4x is 2x squared. antiderivative of negative 4x plus 4 is negative 2x squared plus 4x. I'm doing two separate integrals here with the fundamental theorem of calculus, and I'm going to add the results. Plug in 0.5 here, subtract what you get when you plug in 0.4. With the next one, I got to plug in 0.8 and subtract what I get when I plug in 0.5. So this is getting kind of complicated. I think I can do it right here. Now simplify. 0.5 squared is 0.25 times 2 is 0.5. 0.4 squared is 0.16 times 0.2 is 0.32. That's a 0.18 there. Here, what do we get? 0.8 squared is 0.64 times negative 2 is negative 1.28. Just doing some calculations in my head. 4 times 0.8 is 3.2 minus 0.5 squared is 0.25 times negative 2 is negative 0.5. And this product is 2, it looks like. Almost done. That simplifies to what? 1.92, I think. Is that right? Yeah, I think so. And this simplifies to 1.5. I got 0.18 plus 1.92 is 2.1. And then I'm subtracting 1.5. It looks like the answer is 0.6, if I have not made a mistake. I'm going to assume that I've done it right and go ahead and circle that. That would be then the probability of being between 0.4 and 0.8, the total area that's shaded green here, just to illustrate a use of the probability density function. But maybe we'd prefer, instead of doing all this, maybe we'd prefer finding an antiderivative, capital F, and just doing one subtraction, like that. And that would also give us the flexibility of solving other problems without doing all this. If we could find just one formula for one function, capital F, that's an antiderivative of little f, that would be nice. And yes, again, the CDF is one example of an antiderivative here. And it turns out that I can construct it. Once again, I'm emphasizing the main point of section 6.1, that I'm constructing an antiderivative of little f by integrating it, starting at 0 and going up to x. Notice, just like in the last example, the x is the upper limit of integration. It's not an accident. I'm thinking of the upper limit of integration as being a variable. This is pretty weird, but it is what we want to do in chapter 6. Not just in section 6.1, but especially at the end of chapter 6. I'm integrating little f. What should I call its variable? Last time I called it capital X with the last example, but I think that's kind of confusing. Should I use a little x? Scientists often do. Engineers often do. They got a little x there and a little x there. But to tell you the truth, that's sloppy, and it's so sloppy that I'm not going to do it. I'm going to use a different letter. Like what? Well, anything you want, as long as it's not an F or an X, is probably okay. I mean, I could use a capital X like before. Not a capital F, not a little x, not a lowercase f. A common letter to use is U. Why? Because we feel like it. Just needs something. Okay, it doesn't have any meaning really. It just is there because I need a letter. It's a common letter to use. But how do I do the integral? What do I do here? Just like before, I can think about it with areas, just like I did with the uniform distribution here. I can think about areas, but now I got to think about areas with regard to this picture. By the way, I should have emphasized the fact that this triangular distribution is higher near 0.5 and lower near the end, 0.0 and 1, means that when you use it to simulate data, most of your data is going to be near 0.5, not near 0 or 1. It's going to be denser near 0.5, where this density function is higher. So let's go ahead and think about it with areas. And like before, we need to think about cases. This is going to be a piecewise function ultimately. Easiest case is actually when x is negative. Because when x is negative, the graph is over here is 0. The integral from 0 to a negative number, you could put a negative sign in front of the integral and switch them around again. But it doesn't really matter because the function's 0 over here. So the integral is going to be 0. 0. If x is negative. It's the other easy case is when x is bigger than 1. Why? Because if x is over here, I'm integrating from 0 to x. I get the area under the curve, but this triangle was constructed so that its area equals 1. This is 1 if x is bigger than 1. The next easiest case, which is getting harder, is if x is between 0 and 1/2. Just draw a generic x between 0 and 1/2. I'm trying to find this area because that's what how you define this function as the integral, and the integral gives you the area. Fortunately, it's the area of a triangle. Its area is 1/2 base times height. The base is x. What's the height? It's not x, even though it kind of looks like it's x. The equation of this red line, remember, is y equals 4x. If this is x, this has got to be 4x. Even though it looks like it's about the same length as x. It's because the scales are different on the axes again. Simplify, you get 2x squared. That is the answer if x is between 0 and 1/2. Notice its derivative is 4x. That's not an accident. The equation of that line, 4x, is the derivative of what we got there. Okay, here's the hardest case. Last thing to do today. What if x is between 1/2 and 1? Let me redraw the picture. Here's 1/2. Where should I draw x? Anywhere you want between 0 and 1/2, say right there. The function still is defined by an integral. I'm trying to find the area of this region. It's not as bad as it looks because you can break it up into a triangle and a trapezoid. The area of this triangle right there is a constant, 1/2 base times height. Oh, 1/2, half the total area under the curve. That's a trapezoid. Base is x minus 1/2. This height is 2. What's this height? That height is the equation of this red line, negative 4x plus 4. And that is a positive number when x is between 1/2 and 1. The area here is the base, x minus 1/2, times the average of the heights, 2 plus negative 4x plus 4 over 2. That's the average of the heights. Hang with me here. This does simplify. This is the same as negative 4x plus 6 over 2, which simplifies to negative 2x plus 3. That's got to get multiplied by x minus 1/2. Let me just write that here. X minus 1/2 times, in parentheses, negative 2x plus 3. Sorry, I'm out of room there. That's an x minus 1/2 and a negative 2x plus 3. It's not obvious, But this expression has a derivative equal to negative 4x plus 4. To check it, multiply it out and try. But we're out of time. I'll say it again. This expression, which is the area of this trapezoid. Oh, and that's not the final answer, by the way. I forgot to add a half here. This expression has a derivative equal to negative 4x plus 4, and it also has the same values this function does at 1/2 where they match.